Hi, everyone. Welcome back for the second part of Yuval's talk on PCGs.
Okay, welcome back. In this part, we will cover recent constructions of PCGs for useful two-party and multi-party correlations like oblivious transfer, triples, and more. And all these constructions are based on different flavors of the learning parity with noise assumption. So let me start by recalling what this assumption is. It was first formally introduced by Blam et al. And it was first introduced over the case of the binary field F2, but it can be naturally generalized to arbitrary fields or even rings. So I will present here the more general version of this assumption. If you're familiar with the learning with errors assumption, it's very similar, except that the noise distribution is different. Instead of having a noise that has a low L2 norm, now the noise has a low humming norm, in the sense that you take a small subset of the coordinates and you pick them at random, but otherwise there is no noise, right? In LWE, you have a little bit of noise or Gaussian noise in each coordinate. Here you have an arbitrary or random noise, but in a small number of coordinates. Okay, so that's really the distinction between LPN and LWE. Otherwise, the two assumptions can be thought of being analogous. You also have a secret. You have a public encoding matrix G, and you add a sparse noise vector, which is secret. And the assumption says that if you can only see the public, you can think of this as a linear code G, and the output of this secret times matrix plus noise, then you cannot distinguish it. You cannot distinguish the output from a uniformly random vector of field elements. Okay, so that's the assumption. In terms of attacks, it's typically more conservative than LWE in the sense that there are fewer attacks, like lattice reduction algorithms do not apply here. On the other hand, you need to be careful about algebraic codes or low density parity check codes, which are susceptible to efficient decoding techniques. But in general, unless you're really unlucky with the choice of G, and I will mention a few choices later, the best known attacks for our regime of parameters are really the trivial attacks of guessing a set of coordinates which have no noise, okay, which are linearly dependent and have no noise. That's characterized by the minimal distance of the code. Okay, so this is the assumption throughout this part of the talk, and we will use this assumption for different types of codes, so different choices of the public encoding matrix G. And also, we will also slightly alter the noise distribution. Okay, so once we specify the code G and the noise distribution, then we've specified the LPN assumption over a given field or ring. So this, I will refer to this as a primal version of the LPN assumption. We will see why soon, but let me just say that there is a certain limitation. Just the trivial attacks of guessing a set of coordinates that are linearly dependent and have no noise imposes some restriction on the relation between the stretch and the noise, which basically results in a quadratic limitation on the stretch of one type of PCG constructions based on LPN, and for this we will use a dual form of LPN to get around this quadratic stretch limitation. In the dual form of LPN, which is technically equivalent to the primal version that I've defined before, only for the dual code, here we don't encode, but we compress. So we take a sparse vector, a random sparse vector. We apply a public compressive linear mapping, unlike the expanding encoding function in the previous primal version. Now we apply a compressive public linear mapping, and we want the output of this mapping to be a pseudorandom even given knowledge of the public compressive linear mapping. Okay, so that's a dual version of LPN. It is can be formulated also again over large fields or rings. This public linear mapping can be implemented with conjectured security very fast, even quasi-linear or even linear time. We have good candidates for that. And that's one ingredient that will be used in the PCG constructions I'll describe next, this dual form of LPN. And the other ingredient is something that Elette described in her presentation, which is a compressed way of secret sharing or of additively secret sharing a sparse vector. So if you look at the notion of a distributed point function, which is an instance of function secret sharing, you can think of it as, if you look at the evaluations of, right, you apply the eval function of the distributed point function on each input in the domain, then you get an additive secret sharing of a unit vector, a vector that is 1 in point alpha and 0 elsewhere. So you can think of function secret sharing or distributed point function as a compressed way of additively secret sharing along unit vector. And now you can take any sparse vector of weight W and write it as the sum of W unit vectors. So FSS or DPF give us a compressed way of additively secret sharing a sparse vector, which, as you might expect, will be a noise vector for dual LPN. And in fact, this is something we need. So we actually need to generate this kind of secret sharing where neither party knows the positions of the non-zero entries when we consider PCGs for OLE, for triples, for truth table correlations that we saw before. For this, we actually need the full power of DPF or FSS, but it turns out that we can relax the security requirement to allow one party to learn the locations of the non-zero entries, but not their values. And for this, we can use the simpler puncturable PRF primitive. So this is something that suffices for the case of Vole and OT correlations. And in both cases, the complexity of generating this secret shared sparse vector, in terms of communication, the length of the seed is W times log n. N is the length, W is the weight, PRG seeds. So concretely, if you use an AS-based PRG, then it's 128 times sparsity parameter W times log of the length. And in terms of the time it takes every party to generate the long share of this sparse vector, it takes. So if we do it in the right way, we can avoid the W overhead in computation. So the total computational cost can be roughly n PRG calls. Okay, so this gives us the full cost of generating compressed secret sharing of a sparse vector. Okay, any questions up to this point?
Yes, we have one question about LPN. Mm-hmm. And the question is, are there reductions between LPN and the LWE in the regimes used?
Yeah, no, it's a great question. And I know that even between different flavors of LPN or different flavors of LWE, the reductions are in general very sparse. Even classical assumptions like discrete log, like factoring, you slightly change them. We have the illusion that we have a small number of clean assumptions. We do have clean assumptions, but each of them has many variants. And LWE and LPN, except for extreme parameter regimes, they're generally incomparable. It's a great research question to find more relations between these assumptions. As I said, with respect to known attacks, there are some attacks that can apply, like PKW style attacks. Certain kinds of attacks can apply both to LPN and LWE, but generally LWE parameters are worse because they're susceptible to lattice reduction attacks, which do not apply to LPN. Okay. So let's now talk about Vole. Again, we heard a lot about from Peter yesterday. Recall that a Vole, you can think of it as a kind of a triple where we take a long vector A known to Alice, a scalar X, a field element known to Bob, both are drawn at random. And now we additively secret share AX between the parties. Okay, so it's a shared product between a long vector and a scalar. That's a Vole correlation. And really, the high-level idea here is super simple and natural, right? The idea is let's forget about the original Vole where the vector has to be completely random. And let's focus on a restricted version where the A vector is still very long, but it's sparse. It has a small number of non-zero entries, but otherwise it's chosen at random. And the nice thing about the sparse vector is that, as we discussed before, we can compress the additive shares of A times X, right? Because if A is sparse, then A times X is a scalar, then it's also sparse. Of course, we can reveal A to Alice, but we cannot reveal A times X to Alice. So we can give to Alice a short description of A in the clear. We can, of course, give to Bob X in the clear, it's just one field element. A times X, we need to secret share between the two parties, but because it is a sparse vector, we can use the FSS or PPRF machinery to secret share it between Alice and Bob. Okay, so this is really the high-level idea, the main high-level idea, that a sparse instance of a Vole correlation is compressible. So that's a PCG, a very simple PCG for sparse Vole. And now the only step that is missing is converting a sparse Vole to a pseudo-random Vole. And this is done, there is also a primal version of the construction, which I'm skipping, that has some advantages, but this is the dual version of the construction that uses the dual version of LPN that I defined. So to convert a sparse vector into a pseudo-random vector, it suffices under LPN to apply a suitable public linear compressive mapping, right? So we compress this sparse vector A, say by a factor of 2, using a publicly known mapping, and we get a pseudo-random mapping. And the nice thing is that we can apply the same compressive linear mapping because it's linear, and because we have additive sharing of A times X, we can also apply it locally to the shares of A times X, the same public linear mapping, and now we get really a pseudo-random instance of Vole, where Alice's long vector is the sparse vector A times the compressive matrix, the compressing matrix H. Okay, and we get additive shares of HA times X, and really the key point that makes this a PCG for Vole correlation is that under LPN, the long vector HA is pseudo-random. Okay, so that's it. That's the most basic construction, and this is already super useful for all the applications that Peter described. Of course, there is also the seed generation part, which Peter will cover tomorrow. But that's also something that can be done with good concrete efficiency. And note that the computational bottleneck here is the computation of this matrix H, which, as I said, can be done even in linear time under plausible assumptions. Any questions about this basic construction?
There seem to be no questions at this time.
Okay, great. Okay, yeah, so technically, if you want to consider the primal LPN with respect to an error correcting code, you take the error correcting code whose parity check is this matrix H, whose parity check matrix is this H, so the dual code to the code generated by H. And if you assume that the noisy random code word in this code is pseudorandom, then this construction is secure. So in particular, if you pick H at random, then the dual is also a random code. Then you get the conservative vanilla version of LPN. But for concrete efficiency reasons, we want to choose, matrices H that have better complexity. Cool. So now the next step, which is simple but a bit more surprising, is how to switch from Vole to OT. Right. So Vole is useful, but it's not still not as useful, certainly for general secure computation, as oblivious transfer. And what makes Vole simple is the fact that in Vole we have one of these outputs is short, right? So it's just a small scalar times a vector. In OT seems more complex because in OT both parties have long strings, right? So the correlation, the secrets of both parties are long. Okay, so the idea is really using a similar kind of trick that is also used elsewhere, in particular in the IKMP OT extension. But here we kind of specialize the Vole correlation to get to a point where we can apply a hash function locally and get these pseudorandom OT correlations. So the main idea is that if we specialize the vector A of the Vole correlation, so this is the vector of Alice, right, in the Vole correlation. If we specialize the vector A such that they're taken from the base field, so think of Vole over a field f to the 2 to the 128. We have the freedom to control the choice of A, right? Because A is something that, the dealer of the PCG gives to Alice in the clear. Okay, and then the dealer also computes A times X and secret shares A times X. But we have the freedom to choose A. So instead of choosing it from the big field, the extension field, let's choose A to have 0, 1 entries. And now if we do that, then we get a correlation. The Vole correlation becomes isomorphic to so-called correlated oblivious transfer, which is really the correlation that is generated by IKNP. So it's a bit tricky to say, but if you think of the Vole correlation, AX plus B, where each AI is a bit, then AI, you can think of it as a selector. AI is Alice's vector. You can think of it as a selector between BI and X plus BI, right? AX plus BI selects between, AI selects between BI in case AI is 0, or X plus BI in case AI is 1. Okay, so now if we do this kind of, we call it subfield Vole, then we have a so-called correlated OT correlation, where the Vole sender is an OT receiver now. It knows for each pair of strings known by Bob, Alice knows exactly one of them. Because X is secret and random, it's known by Bob, Alice can only know either BI or X plus B. Sorry, so if we look at what is received by Bob in the Vole, right? So this is AI times X plus BI. Then the Vole sender knows exactly either CI, okay, in case this is BI, or CI plus X in case the receiver, the Vole receiver Bob gets X plus BI. Okay, so we are in a situation where Alice knows exactly one out of two strings that are known by Bob. These two strings have the same offset x between them. So the XOR of each pair of strings is the same x, which is unknown to Alice. But Alice knows one of them and she knows which one. So this, you can think of it as almost like random OT, except that every pair of strings of the sender are not completely uniformly random, but they all have the same random XOR. And then we can convert this kind of correlated OT into a standard random OT by applying a local hash function to destroy this linear correlation. And this is how we get PCG for OT given PCG, or by modifying the construction of PCG for Vole by choosing a from a subfield rather than from the entire field. Okay, so, and this is also known as silent OT extension, PCG for OT. Okay, so in terms of efficiency, it's really similar to Vole. And here we use a binary field. Cool. So, so one can generalize this construction from a feasibility perspective. Now, this part is not practical. We can take any additive degree decorrelation. So basically, you take R to be the output of some degree D map applied to random and independent field elements, and you split it additively between two parties. That's an additive degree decorrelation. And we use a simple tensoring trick to get construction for any such correlation. So this includes standard triples, authenticated triples, OLE. So all of these are special cases. So this gives a general construction under LPN where we take, so we want to generate additive shares of P of R, where P is some degree D polynomial map, and R is a bunch of random field elements. In the construction, it follows along the same lines, except that instead of just doing a compressed secret sharing of a sparse vector A, we also generate compressed secret sharing of A tensored with A tensored with A with 3 times and so on up to the degree D tensoring. What this tensoring means, it means just the vector of all pairwise product A times A is the vector of length n squared that contains of all products of the form AI times AJ. It is less sparse than A. So if A has a Hamming weight W, then A times A can generally have Hamming weight W squared. But still, if we think of W as being a security parameter or even smaller in some cases, then A times A can be practically feasible. Beyond that, it's becoming less and less feasible. In any case, the idea is that now we can express, we want to unsparsify A, so we multiply it by this compressive mapping H, and now we can express the degree D polynomial map in H times A as a linear function in these tensored entries. So we do this compressed secret sharing of all these powers of A, and we can apply local linear mapping to generate additive shares of degree D correlation. So this approach works in theory. It can rely on a conservative version of LPN, but it has poor concrete efficiency, even if we just want OLEs or triples. So degree 2 correlations, and even if we take H to be a very efficient circulant matrix, this approach takes quadratic computation. If we think of N as being at least 1 million, that's the number of instances or the length of the correlations we want to generate, then this is computationally infeasible. It might be borderline feasible if we use a smaller value then. Okay, so how do we handle these correlations beyond Vole and OT in a practical way? So an idea which is borrowed from LWE context or FHE type of tricks is to use not plain LPN but some structured version of LPN for codes that have some are ring friendly in some sense. And a natural attempt is to do the following. Instead of taking sparse vectors and tensoring them, let's take evaluations of sparse polynomials, right? So we can do any linear mapping on a shared vector. So instead of sharing a sparse vector and thinking of it as our vector, let's just share the coefficients of a sparse polynomial. So a polynomial that has a small number of non-zero coefficients. We can again do it in a compressed way using function secret sharing. So we take two sparse polynomials, S and S prime. The evaluations of each polynomial correspond, say, to the AI and BI in the triples, right? So in the triples, we want to have many shared AIs, many shared BIs, and then the products of the AIs and BIs. So let's compress all these AIs using a sparse polynomial S. Let's compress all the BIs using a single sparse polynomial S prime. And let's compress all the CIs, AIs times BIs, by doing a compressed sharing of the coefficients of the product polynomials. So the product of two sparse polynomials is somewhat less sparse, is quadratic. There's a quadratic number of non-zero entries, but again, these numbers in practice, this weight parameter can be 25 or so, okay? So it's not terrible to square it. It's not prohibitive from a practical perspective. Okay, so the good news is that this satisfies the functionality that we want because, polynomials have the nice property that we all love and use, that we can multiply the polynomials, and this corresponds to local products of their evaluations. And also in terms of efficiency, now we've beaten the quadratic barrier of the previous generic approach because we can use FFT to implement all the conversions, right, from polynomials to evaluations, from coefficients to evaluations. We can do it in quasi-linear time, so that's great. So functionality and efficiency are great. The problem is with security, and here we really run into this corner case where LPN assumption is false. So if we use Reed-Solomon codes, then we know that they're efficiently decodable, and LPN assumption fails for such codes. Okay, so this would be the first attempt, and this attempt is almost good, except that it's not secure. It's broken by algebraic attacks, like Berkeley-Welch decoding technique. Okay, so instead, we again follow the LWE route, and we use a ring version of LPN that in fact has been introduced and used before to make LPN-based crypto more efficient. And for this version of LPN, you can think of it as some kind of a twist on a Reed-Solomon code that avoids the efficient decoding, some kind of randomization. Thinking of it algebraically, we consider the ring of polynomials of a big degree n, right? Think of n as the length, the number of instances of OLE or triples that we want to generate. Modulo some other degree n polynomial f, okay, that we will talk later about different choices of f, but let me just say that for the most useful correlations, OLEs and triples, we actually want this polynomial f to split into linear factors, because in this case, we have the same property that we have for Reed-Solomon code. We can think of the ring as being isomorphic. It's homomorphic with respect to the evaluations. Okay, so it's isomorphic to ZP to the n with pointwise additions and multiplications. Okay, but now the construction works almost like the general LPN-based solution, except that here we use the sparse polynomials in the ring, both for generating the secret will be E. It's a sparse polynomial from this polynomial ring. And F is the noise polynomial. Both of them will be sparse. The only thing which is dense is this public polynomial A that we use. This plays the role of the matrix H in the generic LPN-based construction. So this is a dense polynomial which is public, so we can compress it because it has short description. But the secret polynomials, both the noise and the LPN secret, are sparse, so we can secret share them using function secret sharing with low communication. Okay, and the ring LPN assumption says that disjoint distribution, so if you know the public dense polynomial and you don't know these two sparse secret polynomials, then the output looks pseudorandom. For certain types of PCGs, like if you want an inner product correlation or you want a big correlation over, over a big polynomial ring, then we can use an arbitrary polynomial F, but for the purpose of generating OLE or triples, many instances of them, we need F to be fully splittable into linear factors. We do an analysis, this is in a paper from Crypto 20, we do an analysis of security and find slightly better attacks than in the irreducible case, but we generally believe that by adding slightly more noise, we get the same level of security as in the irreducible case. Okay, so better analyzing this flavor of LPN is a good question for further research. It's been almost 2 years and it still stands. Okay, so how do we generate PCG for triples for ring LPN? Here the approach is very similar to the previous one. We just write, okay, so recall that E and F are sparse and A is dense but public. So we can write this is really the vector of the AIs. This is A public dense times E secret sparse plus secret sparse. That's one vector. That's one polynomial, and we want to multiply it by another polynomial, which is A times E prime plus F prime, right? So this is, you can think of it as a polynomial. The first one is a polynomial that encodes the AI in the triple language. This is a polynomial that encodes the BI in the triples language. And we want to multiply them and secret share the coefficients of this polynomial. And opening parentheses, we can see that this breaks into a public part. This is a product of two E times E prime is a product of two secret but sparse polynomials. So if the sparsity parameter is W, we get W squared sparsity. So it's more costly. This sparsity level, quadratic increase in sparsity costs us, but we will see concrete numbers, it's not too bad. And here we have the third term. This is public. So this is cheaper, right? Here we just need to take a sparse vector and here too we have these two products of two sparse polynomials, and finally we have another product of two sparse polynomials. So overall we need to do a constant number of secret sharings of coefficients of polynomials that are either W sparse or W squared sparse. Okay, so we do them via FSS. Okay, and then we can implement the local evaluation expansion in quasi-linear time by using FFT techniques for polynomial multiplication and multi-evaluation. And overall, we get quasi-linear time of generating, right? So the seed length is logarithmic and evaluation time is quasi-linear. Okay, and security is based on the splittable version of ring LPN assumption. Splittable because the modulus polynomial should fully split, at least for this kind of OLE and triples correlation. Okay, so In terms of cost analysis, so here the sparsity parameter is denoted by T. So we need order of T squared with a small hidden constant DPF keys. Here we cannot use a PPRF. We don't know how to use a PPRF. We have to use a DPF. The local evaluation time, if you do it with a generic noise, because of these T squared non-zero coefficients, we need to do T squared instances of eval all for DPF, and T squared times evaluate DPF on the entire domain. So doing this will take us n times T squared, which is bad. Again, think of T's as being like 30 to 50 in practice. But if we choose the noise or the non-zero coefficients, instead of being uniformly random, we choose them from a regular distribution where we split the n coordinates into blocks, and each block has just one non-zero coordinate. So again, this is something that is done quite often in the context of LPN style assumptions. So for this type of noise distribution, we can shave a factor of T and realize the computation in just we can get it in n times T PRG calls instead of n times T squared. Okay, so in terms of extensions, we can handle authenticated multiplication triples with less than 2x overhead. The reason is that we have full control over the polynomials, so we can also secret share these polynomials, the same polynomials, E and F and their products, times some secret multiple that we choose as a PCG dealer. In the Crypto 2020 paper, we present extensions to other kinds of degree 2 correlations, including matrix triples, and also to multi-party correlations. But the extension to multi-party correlations that I will describe in the next slide is a bit more costly and also does not work for the authenticated triples. We'll see why. Okay, if there are any questions up to this point.
Chat is silent.
Okay, good. Yeah, so this is the optimization I mentioned, that if we use regular noise, then the n times T squared can be improved to order of n times T computation time. Okay, so how do we extend it to multi-party multiplication triples? So multi-party multiplication triples are many instances of additive shares of AI, additive shares of BI, and additive shares of AI times BI. What are these multi-party correlations good for? We can use also pairwise triples for the multi-party case, but this will incur a quadratic online communication cost in the number of parties. So each multiplication, if we use the pairwise correlations, we can use triples or authenticated triples between every pair of parties, but this will make the online communication cost quadratic in the number of parties. If we want to make it linear, then we need this kind of multi-party correlation where we additively share AI, BI, and CI between the parties. And then we can get the online. This is especially helpful when we have a bigger number of parties, in which case we get big savings in the online communication. So we can do it in a not completely black box way by relying on the two-party PCG. What we rely, the extra property of the construction of the PCG that we rely on is that we can mix and match. So we can take the same A that we split between one pair of parties and use it also to split it between another pair of parties. Okay, so the same secret vectors that we share. And using this, we can apply, for those familiar with the GMW protocol, a similar trick where we can write the product of the sum of the AIs with the sum of the BIs as the summation of a quadratic number of terms, AI times BJ. We use a two-party PCG with this programmability, this mix and match property to do an additive secret sharing of AI BJ between parties I and J. Okay, because party PI can legitimately know AI, party BJ can legitimately know BJ. This is the additive share of party J, so we can split the product between them. And then we add up the outputs of this quadratic number of two-party PCGs, and we also need to do some re-randomization of the output using this PRG-based PCG for additive shares of zero, the tournament-based that I described before. And we get a PCG for n-party multiplication triples. This construction, unlike the two-party case, it does not work for OT. So we cannot get a binary multiplication triples, which are quite useful if you want to evaluate Boolean circuits, by using the PCG for OT, because the PCG for OT actually does not have this required mix and match property here. So that's an open problem. We don't have a practical way of generating these binary multi-party multiplication triples. And the same for authenticated triples. Here too, the fact that every pair of parties, we cannot take the same global secret and multiply it by AIBJ, because then PI and PJ together, if they collude, they will learn this global secret. So there is a way around it. There are two ways around it. So our inability to generate multi-party correlation triples in a practical way, multi-party authenticated triples in a practical way. One is in an upcoming PKC paper by Abram and Peter Scholl, which according to Peter, I haven't seen the paper, it relies on three-party DPF, which as Elad described, we don't have really good constructions for. And that's one of the reasons that make it somewhat inefficient. It's practically feasible, but not nearly as efficient as the two-party construction for authenticated triples. And a very different approach, in a work that's related to what Henry talked about yesterday. So in a work with Elet, Niv, and Ariel, from last crypto, we show that you can actually, so the speeds approach is to use authenticated triples to get a fast online malicious MPC. And in this work, we show that you can actually use unauthenticated triples, so kind of like semi-honest, and only use a logarithmic amount of extra correlated randomness, which in some cases can be generated efficiently to get full security. So in some sense, we can sidestep the need for multi-party authenticated triples by using the fully linear IOP machinery that Henry described yesterday. Okay, so there is still it's still a work in progress to make the generation of this kind of correlation more efficient, but at least it gives us a way to get the same online complexity that we get from speeds, but using where the bulk of correlated randomness consists of standard triples as opposed to authenticated triples. Okay, so let me give a couple of data points on concrete efficiency, and we'll hear more about that from Peter tomorrow. So if you want to generate Vole or OT, so here's 1 million instances of Vole over 128-bit field, or 1 million instances of 128-bit string OT or bit OT, doesn't matter. So the seeds consist of, again, I'm ignoring now the cost of, I will tell you soon what is the cost of generating them, but for now, just consider the compressed correlated seeds that you need to store for future MPC or 2PC. So it's only 10 kilobytes, and expanding them, at least in our original works, it took 1 second. And this was done by using a matrix H based on quasi-cyclic codes that are also used in post-quantum public key encryption schemes that are being standardized. Okay, so we used a kind of conservative assumption and in fact existing implementations of LPN-friendly compressive mappings that are quasi-linear asymptotically and in practice take 1 second to compute for these parameters. The seed generation is roughly 10 times, so not too bad, it's 10 times the complexity or the size of the seeds, and that's with malicious security. That's from a CCS 19 paper with the usual set of authors and Peter Rindal. And so even the end-to-end cost here is quite low. And in fact, if you look at the computational bottleneck, there is in a really nice recent crypto paper by Geoffroy Couteau, Peter Rindal, and Srini, they show how to use a special class of LDPCs to have a very fast implementation of this compressive linear mapping that takes linear time and reduces this expand time by a factor of 20. The assumption is still somewhat speculative, but it looks very plausible, and there is good evidence for security against known attacks up to perhaps minor tweaks. So overall, if we look at the state of the art, this is the state of the art construction of PCG for OT. The end-to-end cost, even if you don't care about the silent feature or the compressed representation, even the end-to-end cost is like very, very small sublinear communication complexity for a sufficiently big batch, right? So this is like a batch of million OTs. And the computational cost, as I mentioned before, is slightly better than IKNP of this recent implementation. And, one could expect maybe even better constructions to exist. So it's really the fact we're utilizing the fact that we're amortizing over a big number of instances. So we just need, in a sense, to do the opposite of what coding theorists are trying to do. So coding theorists are trying to build codes that can be efficiently decoded. We can build, our goal is to build codes that cannot be efficiently decoded, and almost all codes are like this. So we have much more freedom to choose the codes to be efficiently computable. Okay, if we look at OLE and triples, then computation becomes, both computation and seed size become much bigger by roughly two orders of magnitude, but still very practical. So the seed, even for just 1 million instances of 128-bit OLE or authenticated triples, the seeds are considerably shorter than the outputs. And they take 10 to 20 seconds to expand on a single core. Okay, so if computation is your bottleneck, just throw in a few extra cores. And again, this is just estimates based on a fairly standard implementation, and one could imagine a much better performance with the right kind of hardware support and so on. Okay, GPUs or other optimizations. The seed generation is also more expensive, but not super expensive compared to the length of the seeds, and we'll hear more about that from Peter. And if you compare it to non-silent alternatives for generating triples or authenticated triples like Overdrive, which is the SPID's state-of-the-art implementation, and Leviosa, which uses an IPS-style approach, they're much, much more expensive in terms of communication, and the runtime is comparable. So if you throw in a couple of, either even with a single core or certainly with a few cores, then communication becomes a bottleneck and not computation, and then this PCG approach will be better. So again, all these things have not been fully validated experimentally, but the numbers here are taken from actual implementations. It's just that the whole system was not put together, as far as I know. Okay, so so how much time do I have?
About 5 minutes.
Okay, cool. So Let me conclude by talking about a natural extension of a PCG called the pseudorandom correlation function, or PCF. And this is really what you expect when you consider the analogy with the standard pseudorandomness. So a standard PRG, it's useful, it's good, but it doesn't have the random access feature that you want, say, for block cipher or for a standard stateless encryption scheme, right? It's good for stream ciphers, but it's not good for a standard encryption scheme where you don't want to keep a long state or to update your state. You want to have a key, and now you want to encrypt the message, you just encrypt it. So use a PRF for that, not a PRG. And similarly for PCGs, if we don't want to pre-compute and store all this long target correlation, say 1 billion instances of OT or OLE, and we want to have a short state that will allow us to generate more correlated instances of OT, Vole, OLE on the fly, then we want a pseudorandom correlation function. Okay, so you can think of it as a pair of correlated pseudorandom functions. They have correlated keys K0 and K1, and you can really think of it as a PCG with a huge output length, but where you don't need to pre-compute this output, you have random access. You can generate more instances on the fly as you need them. And again, it's formalized in a similar way. We need security against insiders. You might expect that analogously to the tree-based construction of a PRF from a PRG, we could use a similar approach for PCG. Unfortunately, it doesn't work just because we do not have PCGs for the type of correlations that we will need for such a construction to work. And instead, we need to use FSS-friendly families of pseudorandom functions. Concretely, we need a weak pseudorandom function, which is like a standard pseudorandom function, except that security only needs to hold on random inputs. Okay, so you can use a random oracle to bridge the gap between the two. And so if you have a weak pseudorandom function class, F sub k, such that we have a good FSS scheme for this class of functions in the sense that Elet described. So if we can additively split a function from this class of pseudorandom functions into two additive shares that have a compact representation, then we get almost immediately a PCF for OT and Vole. And using a slight extension, we can get also triples and Ole. And the reason, and for simplicity, let's assume also that this class of that the FSS scheme is also the function class is also closed under scalar multiplication. That I cannot only share a pseudorandom function f sub k. Think of the output as being over some finite field, but I can also secret share using FSS any scalar product of the function. Okay, this is not needed for the OT or OLE application, but think of it for simplicity. So if we have this weak pseudorandom function family and a function secret sharing to secret share functions and their scalar multiples, then we can generate a PCF for Vole in a really trivial way, right? We just pick a pseudorandom function from the class. We secret share it between the parties using the given FSS scheme. And then we use the same FSS scheme to share this scalar product, x times the function, right? This is really a random access instance of Vole. You have a random function, which is a compressed way of expressing an exponentially long random vector, and a random scalar vector x of this function. So we give x to one party, we give the function f sub k to the other party, and we use FSS to secret share the product of x times f sub k between the two parties. Okay, so the real challenge here is really finding a concretely efficient function secret sharing scheme for a family of secure, weak PRFs. And for this, we introduce a new construction of weak PRFs, which is really surprisingly simple. It's a new construction, but we spend a great deal of effort in analyzing its security with respect to known classes of attacks. And essentially, you can think of it as doing the following. You start by XORing the secret key and the input, right? So a PRF takes a secret key and an input and produces an output that should be pseudorandom. So the construction applies a sparse polynomial over F2 to the XOR of the input and the secret key. What kind of sparse polynomial? This polynomial. Okay, so essentially just take a bunch of security parameter, many monomials of each size, and you're done. Okay, so this is like taking a security parameter, many monomials of size 1, XORed with security parameter, many monomials on you can think of fresh sets of inputs of size 2, of size 3, and so on, up to size, the input size. Okay, so this is a construction, an explicit new construction of a weak pseudorandom function candidate. There are two things to argue. First of all, that it's secure. So we argue security, again, with respect to known attacks, but you can also think of it as a natural variable density version of a standard LPN. I will show it quickly in the next slide. And the other point to notice is that this construction is FSS friendly because of the way we use the secret key. The secret key just controls which inputs are being negated. So we can think of each monomial applied to this input XOR the key as just a secret point function. Okay? So we can use a DPF for each monomial of this sparse polynomial evaluated on the input XORed with the key. So this is what makes this construction FSS friendly. And in terms of security, it does have a 2 to the square root n attack, where n is the input length. So the parameters cannot be too small. We cannot get it with 128-bit input. But we have a version of the construction that we conjecture to achieve this level of security. And beyond the PCF, which is our main motivating application, you can use the same assumption to get something known as related key attack security under XOR, which is very challenging to construct from standard cryptographic assumptions. So that's another byproduct of this assumption, that we get this useful primitive. Okay, this is just in a picture how the variable density LPN assumption, which is equivalent to the security of the weak PRF, look like. So it's the same as the dual LPN that I've shown before, except that we change both this matrix H, the compressive matrix, and the noise distribution to have this exponentially variable density. So we start with, think of W as being roughly security parameters. So we have a first block of size 2W that has W non-zero entries. In each row, it's picked independently. Then we have, we go to the right, we double the block size, and we also double, but we keep the number of non-zero entries. So the sparsity level decreases exponentially, and the same for the LPN noise. Okay, so that's essentially an isomorphic way of showing this previous explicit polynomial-based presentation of the construction. Okay, so to give a data point on concrete efficiency, it is slower than the PCG constructions I've shown before, but it's still practically feasible. So the keys, if we want to generate OTs and voles on the fly, the keys are not super long. So we have two versions of the assumption, conservative and aggressive. The conservative version has a provable security against the all known attacks, and the aggressive one has some conjectures in it. But at least from the aggressive version of the assumption, the keys are not too long, and we can generate something like 20K on a single core, 20K instances of OT or Vole per second, which is not bad, and you can, of course, speed it up using multiple cores. And Peter will tell us tomorrow about a different, very different approach for a practically feasible PCF. It is really, really good in terms of setup and key size, but it is worse by I think 1 or 2 orders of magnitude in terms of evaluation time than this variable density LPN-based construction. Okay, cool. Okay, so just very briefly, one cool application of this PCG machinery is that now you can assume that you have many OT correlations, random OTs for a very small price. You can do certain things that were previously quite expensive. So for instance, you can, and again, this is not completely trivial, this appears in a recent crypto paper, but you can generate from OT correlations with very small amount of communication, you can generate the type of correlation that allows you to swap from mod 2 representation to mod 3 representation. And we have a line of MPC-friendly symmetric crypto primitives, PRFs and other versions. So you can get a stronger version of OPRF than what Peter described based on Vole. So things that can be used for any application of OPRF. Under some, of course, some new assumptions, but the distributed evaluation of these types of PRFs and other symmetric crypto is being sped up dramatically by using the PCGs for OT. So we can get, the bottom line is that distributed symmetric crypto or MPC-friendly symmetric crypto, it's a very useful thing. Think of every application of symmetric crypto you could imagine this being distributed. PCGs help us a lot together with specially tailored implementations, new versions of symmetric crypto, including those that use switching between mod 2 and mod 3 linear functions. This combination is very powerful, and I expect it to find applications in the future. Okay, so open questions. A lot more to be done, and certainly will be done in improving current PCG constructions. We want to deal with more general correlations. So I think Let even mentioned the challenge. We don't know how to compress. We can compress a single big truth table correlation, but we don't know how to compress many truth table correlations or many FSS keys, right, that we can use for FSS gates of the type, say, computing a ReLU gate for neural net computation, right? We really want to compress many of these correlations, FSS correlations that enable us to do fast ReLU, but we don't know how to do it without relying on I/O, in fact. We don't know how to generate garbled circuit correlations. Another amazing thing, if we could compress somehow a garbled circuit correlation, this will be almost like FHE. We don't know how to do it, again, without relying on I/O. The multi-party case, as I said, we're still behind what we know in the two-party case. In particular, we don't have good solutions for binary triples, even non-authenticated binary triples in the multi-party case. And we don't have a very good solution for authenticated triples in the multi-party case. There is still room to improve the seed size, the expansion time, the seed generation. And if we go back to the mini-crypt world, if we look at this N-choose T overhead for linear correlations of Shamir secret sharing, we don't know how to avoid it. If we want Shamir to, say, to compress many independent Shamir shares of random secrets for a big number of parties, we don't know how to avoid it, even if we are willing to assume FHE or LWE, right? So that's an open question, even on the theory side, let alone practical side. A better understanding of LPN type assumptions will introduce new flavors of existing assumptions. So definitely there's more room for cryptanalysis and provable security. And PCFs are still significantly behind PCGs, so there's much more to be done on this front. And that's it. So any questions?
I think there are still no questions. Everything was very clear.
Okay, great. So yeah,